Alright, so in this video we're going to take a look at the practical analysis of the boost converter. In a previous video we looked at the sort of conceptualization of the boost converter based on the sort of canonical switching cell, as they call it, and we looked at how it works as a concept, but now in engineering we need things to be practical, and so we need to be able to analyze the different components of the circuit and to be able to design it and actually understand it and control it and use it. So to do that, we need to understand how the thing operates in a practical sense. So this is the circuit that we have, and you should be familiar with the circuit at this point. And if you're not familiar with the sort of workings of the boost converter, I'll link the video in the description so you can figure out how we conceptualized, or conceived, I guess is the correct word, this converter from all the things that we were trying to do. So, as always with this type of analysis, we're going to start with the inductor voltage, because the inductor voltage gives us a good idea of what's going on. We'll look at the inductor voltage and its ripple, and then we'll also look at the capacitor, the inductor voltage and its current ripple, I should say, and then we'll also look at the capacitor voltage and the output voltage ripple, and then we'll look at this this concept of the conduction modes and the continuous conduction mode and the discontinuous conduction mode, and so on. But first, before we do anything, we need to sort of plot some waveforms. So VL. So from 0 to dt, we imagine that the switch is on. If the switch is on, there's a short placed across the switch. I keep saying switch, but I mean transistor. The transistor is on, meaning there's a short to ground, meaning VL equals VDC. And VDC is less than VO in this case, right? So keep that in mind. So VL equals VDC, let's say, is that. Okay, so this is VDC. And then when the switch is turned off, then the diode is forced to turn on. And so the diode is forced to turn on, then we see that the voltage across the inductor will be VDC minus VO, right? So VDC minus VO will actually give you a negative value, since VO is larger than VDC in this case, because this is a boost converter. So the waveform looks something like this, is the point. So this is going to be VDC minus VO. Okay, and that's that point. Now here, I've drawn this apart a little bit larger because we're going to draw a couple of different currents here. It's not enough for us to just draw IL. We're going to also need to look at ISW and ID, I guess we can call it. I haven't really labeled that here, but ID, because one of the key distinctions between the buck and boost converters is that the inductor is not connected to the output directly. So in a buck converter it is, so the output average current, for instance, is the same as the inductor average current. In this case it's not, so the output average current is actually equal to the diode average current. And so we need to be able to translate between the inductor current and then the diode current. And to do that we need to understand how the currents are sort of distributed between the two parts of the switching cycle. So, I mean, leaving all that aside for now, we have the typical behavior. I mean, we have a ripple, so we have a constant voltage applied to an inductor, so we have some ripple like this that goes up, and then we expect, again, it comes back down to the same value here, so it should look something like that, right? Hopefully I can get rid of that, if this will let me erase. Sure, great. Okay, and then it'll also continue up. I mean, it's continuous, right? So it just keeps going like this. So there's no issues with that. We don't really care too much about that, but we're more concerned about this. So this is IL. Now this obviously has a ripple. This value is we called in the previous video delta IL has a ripple. It also has an average value. And so this average value would be something like this. And we can call this, I guess, capital IL, or sometimes you'll see IL with a sort of overline or overbar, whatever you want to call it. In any case, we'll call it IL capital like that. And so we have this average current, we have this ripple current, but what is this ripple current? We can define the ripple current in terms of the voltage that it's applied to it. So if we look at this interval 1, so from 0 to dt, we see that VL, we know, I should say, that VL is L di by dt, And if we rearrange this, then we'll get that delta IL equals VL delta T over L. And the D turns into delta because what we're doing in this case is we're considering a wider sort of time span as opposed to instantaneous or infinitesimally small sort of concurrent durations. We're thinking about a very large or a larger time than a small time. So we change the D to a delta. But what we end up with after we do all that is we know what VL is. We know VL is VDC. We know that delta T is DT, capital DT I should say. And so then we know that delta IL in this case is VDC over L dt. And this is the expression for the ripple current for the boost converter. So if you want a certain ripple current, you can design it. You can pick a certain inductor based on that, or if you have a certain inductor and you want to know what your ripple current is, you can calculate it based on this equation. So this is a sort of design equation that we use for this converter topology. But the next thing I want to talk about is the voltage ripple. And so to understand the voltage ripple, we need to break up this analysis to understand the diode and switch current as well. So while this switch is conducting, the switch current is non-zero, and while the diode is conducting, the diode current is non-zero. Meaning, if I represent, or I mean, I can draw it, I guess, with purple, let's say. So the purple will be the switch current. So while the switch is conducting, the switch current is equal to the inductor current, and then it goes down to zero. And then it stays zero for that much time. And then it goes up again. I don't know how clear that is. Maybe that's a bad idea to use that color. Let's use this pink color instead, but then that interferes with it. Oh, that's okay. So this is going to be, we're going to call this ISW. So I'll just do that. Well, that's a little misleading, isn't it? So maybe we just say ISW is that. Okay, so this pink current is ISW. And it's zero here. So it's zero prior to. And then the switch turns off after DT, and the diode starts to conduct. So we have some diode current. And the diode current is the same as the inductor current. So then for that duration, you basically have, and the reason I'm drawing it slightly below is so that you can actually see it, otherwise you won't be able to see it. But in reality, I mean, it's exactly the same. And so you have something that kind of looks like this. And so this is zero at this point. And this we can call ID. And so the point I'm trying to make here is that the switch, the ripple in the switch, and the ripple sort of here, and I don't mean ripple in the strict sense, I mean like the sort of change between these values, because this instant, I'm assuming it instantly goes up and then instantly comes back down, right? So this sort of difference, this ripple current, a delta IL, is actually the difference between these sort of slopes as well. So it appears there as well, is the point. So what we see in is that the slope for ID is also equal to VDC minus VO over L, as it would be for the inductor current. And we see that the slope for the switch current is also equal to VDC over L, as it would be for the inductor current, as we've seen when we just calculated the ripple current, right? So that's useful to us. So then we know then that the that ID will have this type of a waveform, and we can analyze the capacitor voltage to determine what the capacitor voltage ripple, or how we can write the capacitor voltage ripple in terms of the circuit parameters. So what do we have then? We have, of course, let's maybe draw the circuit. So you have a diode, you have a capacitor, you have a resistor. Something like this, right? And I don't really care about the rest. I just care about this current ID is here. I care that IC absorbs the entire ripple, and I care that this is basically whatever the average of ID is, I guess, right? So this is IO, or I should probably write it the other way. So IO is equaling to ID. So IO equals ID. So whatever the average of that incoming current is, will have to be the average current at the output. So again, this is not the inductor that we're concerned with. In this case, we're concerned with the diode, because the diode is connected to the output now. So what does this actually tell us? So let's imagine from this duration of 1 minus dt, which is this time here. So between here, this is 1 minus d times t. And in this duration, the capacitor is going to do something basically. And what is it going to do? It'll charge or it'll discharge depending on the direction and the polarity of the current. In a case like this, we see that the IC is actually the difference. Well, it's the entire ripple. We're assuming it's not the difference, so I probably shouldn't say that. In any case, the voltage of the capacitor can be defined as follows. We know this. We know that IC is C dV by dt, and so we know that IC is going to be equal to delta ID, and this is going to be C delta VO by delta T. Right? So now we can rearrange this and we can determine what it is that's actually going on. So at T equals dt, right? So that's this point here. At this point here, I have a certain value. I have ID equals VDC over L dt, right? That's the value of it there. Because that's how much this current has risen from the beginning of this period to the end of this period. That's what it is there. And then I know that at T equals T, so that's at the end of the period here, I know that the diode current has basically started from an initial value of VDC over L dt, which is what it was previously at T equals dt. So this is dt, and I know that I should probably push this up. That this is dt, and this should be minus the slope here, which is VDC minus VO times or divided by L, times whatever time that thing goes for. So I know this is going to be VDC minus VO over L times 1 minus dt. Okay, and so you have this expression here. And you know then that delta ID, or the change in ID over that time, is going to be minus VDC minus VO over L 1 minus dt. All I've done is I've taken this second part thing. So we have this, and we have this one. So I've taken, we can call this 1, we can call this 2. I've just said 2 minus 1, and I end up with this expression here. So then I have delta VO is equal to delta ID delta T over C, and that gives me minus VDC minus VO 1 minus dt times 1 minus dt, and the first one comes from the expression, the second one comes from the actual time, and this will be divided by LC. And then I can take this whole thing, I can simplify it, I can do a bunch of different things to it, and I can, overall, I'll end up with delta VO over VO is equal to d 1 minus d squared. Well, we can use f, I guess, if you want in this case. And so you can say f squared divided by LC. And if you saw the previous video where I discussed the buck converter, I rearranged this and simplified it in terms of an FC. You can do the same thing here if you want. I decided to leave the equation in this form for this case, but you can also write this LC, so you can write FC equals 1 over 2 pi root LC, and then you can basically substitute this, you can turn this into FC squared times 2 pi all squared, and this is going to be 1 over LC. Then you can substitute that in there and end up with some expression if you'd like. I decided not to do that for this case, so I mean, you can if you want, it makes no difference, whatever really you want to do. And I should also mention that there is a negative sign here, but I've ignored the negative sign because all that really tells us is that the direction of the ripple is sort of opposite to the direction of the current. So the negative really doesn't matter. If you have a negative ripple or a positive ripple, it doesn't make a difference. It's just a matter of the direction, really, that counts in a situation like that. And so the last thing we should talk about here is the concept of continuous and discontinuous conduction mode. And so we saw already for the buck converter, if you haven't seen that already, I've linked that video as well. And so in the case of the buck converter, we saw that discontinuous conduction mode essentially happens when your current hits 0. So let's imagine that this is going to be our period, this is dt. So your minimum current ends up being 0. So your IL min is now 0. So if we have this is IL max and this is IL min is 0. And so if we go back up to our other waveforms, this is continuous mode, right? So this is the continuous conduction mode. And the continuous conduction mode, again, just simply implies that the current conducts through the inductor continuously. So this current, this blue line, never reaches 0. But what happens sometimes is this average will decrease. It'll start to drop because your output conditions change. And so what happens is this lower value here, this IL min right here, so this is IL min, that IL min value might hit 0 or go below 0 actually. Well, it can't go below 0, but like if it were to continue, it would be below 0. But once it hits 0, you're at the boundary between discontinuous and continuous conduction modes. And it's not a bad thing. I mean, some people, depending on the application, some people actually want their converter to be in discontinuous conduction mode. It's easier to design for in certain cases. In certain cases, it's not. It's a trade-off, as all things are. But this is something we need to analyze as well. So this is continuous conduction mode. And in continuous conduction mode, we know that the output over the input, or the conversion ratio, is 1 over 1 minus d. And in this case, it's not 1 over 1 minus d because the whole situation changes. So this is the boundary, okay? And so for this condition where we have IL max or IL min equaling 0, you have a corresponding average current, right? This average current, this is the inductor current, so this has to be IL. And so the boundary, which is sort of defined as when the minimum current is 0, corresponds to the average being equal to ILB. ILB, B being boundary, right? So this is the boundary inductor current. It tells you where the boundary is between continuous and discontinuous conduction modes. So we can say then that when IL min equals 0, we can sort of define where the boundary current is. So how do we find the boundary current? So first of all, we know that in general, IL min is going to equal the average IL minus 1/2 of the ripple delta IL. But if this goes to 0 and this IL becomes ILB, then we end up with ILB equals 1/2 delta IL. And we already solved for delta IL previously, so we know that this is going to be equal to VDC over 2L times dt. And this is your boundary current for the average inductor current. But the problem is the average inductor current is not the current at the output. The average diode current is what goes to the output. So we have a bit of a problem here. Because we want to compare the corresponding currents. You can't compare the output current to the inductor current and then conclude that it's continuous or discontinuous. You have to compare the average output to the average output boundary and the average inductor to the average inductor current. The average inductor current to the average inductor current boundary. The boundary should be compared with the actual current, not the You can't just pick and choose whichever ones you want. So we have a bit of a situation here. And so the situation can be resolved fairly simply. And how do we do that? So what we can do is, we know in a boost converter that VO over VDC is equal to 1 over 1 minus D. Okay? And we know that by conservation of energy, or whatever you want to call it, power balance or whatever, we know that VDC IDC should equal VO IO. And this is the DC side current, or I guess DC source current. So IL basically in this case. So conveniently enough, I can actually use VDC and VO to relate IL to IO. So I don't need to go through all the analysis of figuring out what's what in the middle, in the sort of intermediate parts. I can do that too, but this is a simpler approach. So what I'm going to do is, and we've done this before already, is we know that VO over VDC is actually equal to IDC over IO. So the reciprocal of this ratio is going to give us the current conversion ratio. So then we say that IO over IDC is going to be equal to 1 minus D. And what that means is that it's the same as true for the boundary current, right? So that means ILB is going to be equal to, is equal to, I shouldn't say is going to be equal to. I can write this in terms of VO, and it's usually a good idea to write this in terms of VO because we're going to deal with the output boundary current. So if I have the output boundary current, it's good to write it in terms of the output voltage. So first what I'll do is I'll write this in terms of VO. So I'll write VO over 2L D 1 minus D T, that's ILB. And then I know that IOB over ILB is going to be equal to IO over IDC, basically. And so this implies that IOB should be equal to VO over 2L. Well, we wrote the D first, didn't we? So D 1 minus D squared T. And this is your output boundary. Now I can compare the output current with the output boundary current in order to determine which mode of operation I'm in. Before, I can't compare L to O, right? It's not the same current. You have to compare the actual current to its boundary value. So you check IO with, or you compare IO with IOB. If IO greater than IOB, this is CCM. If IO less than IOB, this is DCM. Now, the last thing we have to look at here is the conversion ratio while this is going on, right? So the conversion ratio in a situation like this will be, it'll be a similar process as before, but essentially IOB, first thing we'll do is we'll look at IOB max. So the maximum boundary current that we have happens when D equals 1 over 3. And the way you look at that is you can take the equation, you can take a derivative, and you can set it to 0, or you can just plot the function and see what happens. But it happens at D equals 1 over 3. Okay, so IOB at D equals 1 over 3 is IOB max, just so it's clear. And if you do that and you simplify, you sub it into the equation that we just had above. So you substitute 1 over 3 into this equation, and you simplify the result, you'll get this is 0.074 VO over LT. It's a really odd looking number, or odd looking equation, I know, but it's basically, it's a condition, right? So 0.074 is what all of the things sort of simplify and reduce to. Now we have these waveforms for the inductor voltage and current, which we should also look at, because these will give us insight about what's going on, so we can actually analyze and develop an expression for the conversion ratio, or at least the duty cycle, and then we can find out what the conversion ratio is. So maybe we can ignore that for now, and we can define, this will be dt, and this will be the next thing, and then this will be the next thing. Okay, so what we're going to do is we're going to plot here VL. And so if we're plotting here VL, we have during this time it's VDC, during this time it's VDC minus VO, and then during this time it's going to go back up to 0 because the inductor current is 0, right? So you can't have a voltage across that. And then it'll go up like this again, and it'll keep going. So what's what? This is VDC, this is VDC minus VO, and this is obviously 0. don't really need to write that, but we can just for the sake of consistency. Now, the current. This is the more important thing, I guess, because it actually shows us this more, well, I guess this is pretty obvious behavior too, but this is the more indicative of the two, I guess, because the conduction is, after all, defined in terms of what the inductor is doing. So then there'll be a 0 time. And as we've done in the past, this will be dt between this part. This will be delta 1t, and this will be delta 2t. And the way you can find these is as follows. So the slopes don't change, so this is still VDC over L. This is still VDC minus VO over L, as far as the slopes are concerned at least. And from the volt-second balance, on this inductor voltage, what we can say is that VO over VDC is equal to delta 1 plus D over delta 1. And again, what you would do is you would take the average. So you would take this area, add it with this area, and then, set the whole thing to 0, and you'd get that expression. Now, from this expression, from this waveform, we know this is the average, roughly, let's say. So this is the average IL. And again, we're going to say base times height. And I say again because we did this in the buck converter video. We're going to say base times height divided by 2. Divided by the period is going to give us the average. So the base is what? It's delta plus, D plus delta 1. And then the height is VDC over L. And then we can simplify the whole thing that way. VDC over L times dt. So this is, and then divided by 2, so this whole thing will be VDC dt times d plus delta 1 over 2L. And this is the average current, inductor current. So we can then use the current conversion ratio, and using the current conversion ratio, we can show that IO is equal to VDC over 2L d delta 1t. And we have a bunch of equations here now. So we have, what do we have and what do we want to do? We have this equation here. Let's call this 1. We have this equation, well, no, not this one. We have the IO equation here. We have this 2. And so we can use this equation, along with this IOB. I guess this should have technically been 1. But we can call this, let's call this 0 just for fun. 0, 1, and 2. So we have equation 0, we have equation 1, and we have equation 2. And we're going to use these 3 equations, and you can substitute them into one another, manipulate the results, and do a whole bunch of fancy stuff. But the end result that is important to us is that D is equal to 4 over 27 VO over VDC times VO over VDC minus 1 IO over IOB max, all under the root. And you're going to say, why is this written in terms of D? Because I thought we were supposed to be talking about conversion ratio. And we are. But the thing you have to understand is you can determine this delta in a fairly straightforward manner once you have all this understood. And whenever we're in practice, whenever we're working with this kind of stuff, VO is usually held constant. You don't vary your conversion ratio very often. You vary the duty cycle, and that usually in turn varies the conversion ratio. So having an expression directly for the conversion ratio is not necessarily a useful thing for us, but having an expression for the duty cycle is very useful, because your controller, in response to any disturbances, is always going to act so as to maintain whatever reference you give it. And so if the reference you give it is to always maintain a certain output voltage, it'll vary the conversion ratio through D. So if you have a closed form expression for D, you're actually much better off in that case. So that's kind of why we've done it this way here. And I know in the buck converter video, I know we left it in terms of VO over VDC, but that was it was a neater expression, and you can rearrange that expression fairly simply. In this case, we've decided to do it this way. Again, there's no one way to do it, and you can do it in multiple different ways. The result is the same at the end of the day. So what did we do here? We did a bunch of stuff. We looked at the continuous conduction mode operation of a boost converter, developed the ripple equation, and then we developed an equation for the capacitor voltage ripple, or capacitor depending on what you're looking for. And then we looked at this boundary condition and this boundary current. The boundary current is a very important concept, so this should be very well understood. And we'll look at some examples in later videos as to how this can actually be properly used when analyzing circuits. And then we had a sort of output version of the boundary current. And then the last thing we did was develop an expression for this duty cycle when operating in the discontinuous conduction mode. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.